So this is week 6, lecture A. Next lecture B. We are going to continue the discussion about the controllability observability. So I'm thinking about a midterm. Okay, midterm. I'm thinking about giving you a midterm questions you can take home before spring break. So you'll have a perfectly destroyed spring break. But remember, spring break is never for graduate students, okay? Spring break was designed for undergraduate students. So, last time we did this few things about basis change. Actually, last time basis change, then duality, then LTI system. And we talked about the LTI system and controllability and if and only if controllability metrics. Talking about observability matrices, and then we discussed about model controllability. This is also a very important concept. We talk about distinctive eigenvalues and distinctive eigenvectors. So that's easy. Easy to think about it. So then we define V vector. W vector is the inverse of V vector. V vector is a right eigenvector. W is a left eigenvector. So then we can make the X diagonalized into Z such that you can see that this is Z dynamics in the Z coordinate system. Okay. You are going to see that this is a nicely diagonal. By saying diagonal means there's no coupling between each other. So we just, I do my way, you know, there's no coupling between other coordinates. Make sense? So if a system can be diagonalized, then the control structure will be easier in the future to design. So LTI system with distinctive eigenvalues is controllable if and only if the W times B, and this W times B, you don't have a zero rule, okay? That makes sense. If they have a zero rule, that means this variable Z, let's say K, will not be influenced, not be able to be influenced by control if WB has a zero role, okay? And observable if and only if C times V has no zero column. So then that's very intuitively you can see that. So we have seen many examples on that. So we talked about model controllability, talk about observability regarding repeated eigenvalues. You have work diagonal Jordan blocks, okay? But it's still not very easy to do. Then we find out there's a very beautiful, elegant Hautus test. So this part is the main part for today. We're going to review those repeated eigenvalues, okay, in terms of model controllability and observability. So chapter 9, chapter 13 is what we need to do. Okay, let's forget about distinctive eigenvectors, but let's assume that we cannot diagonalize the A matrix, but we can always make A matrix like this, diagonalized. So you find out similarity transformation to turn this A into a diagonal of J, the block diagonal of the J, okay? Go back a slide, so you will see you end up with J. So it's not fully disconnected, distinctive, fully diagonal, then you have a block diagonal, okay? So again, you have WB and CV here, and you have those building blocks. Each building block is a J, okay? Okay, building block is J. So then the left eigenvalue is V is the W inverse. So then you can introduce that. So then it's the same idea. You have WB and CV, WB and CV. But in this case, how are you going to check controllability, observability? Here is the same thing, but it's a little bit different, in the sense that for lambda, for any distinctive lambda, you have a multiplicity, okay? Multiplicity, you have repeating. But those multiplicity also contains geometric multiplicity, okay? Algebraic multiplicity is just how many of them. You have geometric multiplicity, like how many blocks, how many Jordan blocks. Make sense? So I want to remind you one thing again. So this is a week 6. So we're going to talk about Hautus tests. So basically we're talking about a matrix A that may not be a kind of diagonalized, but it could be diagonalized by the J is Ji. I equals 1, 2, 3, 4, no, until P. So these are the number of it's called block diagonal. Block diagonal Jordan blocks. Okay, Jordan blocks. So yeah, you make that one, and x dot is this to this. You do that, you turn the x into z coordinates. Then the z dot becomes a jz plus wb. Okay, and your y is cv z. Okay, cv z. So then controllability, observability, we don't have to do this one. We only inspect this one. But still need to refer how this is repeating. There are examples to follow to impress you, something you don't really learn in many other linear system books. Okay. So that means you check the last row of each Jordan block containing a lambda as linearly independent. And if it is the first column, all the CVs, okay, all the CVs corresponding to the first column of each Jordan block containing lambda. So this you should remember. However, you better to have an idea. Let's see. So this is easy to understand. You have distinctive eigenvalues. So you have 1 and A. If A is 0, that means the control U will not affect x1 at all. Okay? So because it's 0. So when A is 0, it's not controllable. The same thing is true that B is 0, then x2 is not observable. So the same idea. Okay, so I hope this is clear, right? This is clear. However, if you want to see that so both modes are controllable. But this one, you are going to see that if you put this is a Jordan block, that you are repeating, okay, you are repeating in here. So then you have A and B. So then in this case, if A is 0, it is still controllable, okay? If B is 0, it is still controllable, okay? Compared to this case, compared to this case, okay? Oh no, I think we need to back. Compared to this case, okay? Compared to this case, any of them 0, then no. So this is called modal controllability and observability. So this is of course the simplest case. And in the time behavior, is e to the power of 1 and t times e to the power of t. I hope you get familiar with this. And so both modes are now controllable and observable. So now let's take a look of this one. And I don't have a Jordan block. It's just a repeating. So in this case, you have two Jordan blocks, right? So this is a Jordan block. This is a Jordan block, right? And they are the same. Okay, they're the same. So in this case, okay, it's not controllable for any of the A. Okay, it's not controllable for, not observable for any of the B. Why? Because controllability grammar will give you A1 and A1 again. Okay, A1 again. Because A is an identity, so it's not going to influence them at all. So this is rank 1. Rank 1. Okay. I hope these three cases will give you a very good idea about controllability problem. So one is called 1 is called 1, 2. Another system is 1, 1. Another system is 1, 1, 1. Okay? And of course, B is A1. A1. Then to the 0 in X dot. So this is a multiplicity of 2. Geometric and algebraic multiplicity are the same. Okay, both are 2. But here, algebraic multiplicity is 2. Geometric multiplicity is 1. Okay? And this one is distinctive, okay? Distinctive. So this is perhaps a little bit surprising, but to me it's very normal. So I hope you distinguish these three cases, okay? So if you have a Jordan form, so let's see this one. So you have a Jordan form. Let's do a partition, okay? So we can, from this one, you can see it's a JI, okay? It's a JI. So actually it's this one. So you have Jordan block in here, or you have two distinctive eigenvalues. One is 2, another one is 1, okay? So what is a Jordan block? Okay, you have 5 blocks, okay? 5 blocks. So 1, 2, 3, 1, 2, 3, okay? 4 and 5, okay? 1 and 5. For the first eigenvalue, I have 3 blocks. The second eigenvalue, I have 2 blocks, okay? 2 Jordan blocks. So there's a JI, okay? Okay. Interesting. So I want to understand, this is my B matrix, okay? This is my C matrix. So it's like 3 input, 3 output. Why? Okay, 3 output, 3 input. 3 input, right? 3 input, 3 output. How many states? 1, 2, 3, 4, 5, 6, 7. I have 7 states. Okay, 7 states. Okay, so let's check controllability. Is this controllable? Okay. So if I give you something similar, you should be able to tell this is controllable. But how to do that? Recall what we said. We said the system is controllable if and only for each distinctive eigenvalue. The last row, okay, the last row of this WB matrix corresponding to the last row contain this lambda are linearly independent. What does that mean? Which row? 3, 2, 1. This row is a WB, okay? For this guy, this one. Okay? This last row is 1, 1. This last row is 2, 1, 1, right? So the first eigenblock, first Jordan block, the last row corresponding to WB like here. This Jordan block, last row is also first row is this one. This one corresponding to this 3 to 1. So then you get a 3 by 3 row, 3 by 3 row. We want to check if we can tell if the two eigenvalue, okay, is the mode controllable or not. Only if and only if we check the 3 by 3 matrix that is fully ranked, okay, fully ranked. So the rank is 3, is the 2, 1, 1, this is 2, 1, 1, 1, 1, 1 is here, 3, 2, 1 is here. Put this as a matrix in here, check its rank. The rank is 3, which means the determinant is not 0. Okay? So therefore, that mode is controllable. Okay? Let's check the next mode. You have 1, 0, 1, 1, 1. So this is fully row ranked. So I have 2 rows, then if rank is 2, then it's full rank. It's full row rank. Full row rank. Okay. That means the rank is the same as the number of rows. Okay. In this case, this is all fully controllable. So the both are controllable. But it's possible that this is 1, then the overall system is not controllable, but we know which one is not controllable and which one is controllable. That's called modal controllability. You can tell, zoom in, can tell more about this controllability. That's why doing this kind of diagonalization transformation is useful. You can have a more detailed insights about the system controllability. Same thing here about observability here. So we are going to do the first, for each Jordan block, the first column. So it's 2, 1, 1. Okay, so it's a 2, 1, 2, 0, 2, 1, 0. Then it's 1, 1, 1. Then it's corresponding 3, 2, 1. Okay, so then I have a matrix, and this one it happens to be rank is not 3, so it's 2. Therefore, overall system is not observable. But I can tell which mode, which model, okay, which mode is not observable. It's the mode, all the modes corresponding to the eigenvalue 2 is not observable. Okay. Then next we are going to check this one, and it's fully column rank. I have 2 rank. Column is 2. Number of column is 2, and the rank is 2. It's called full column rank. So this is observable. So overall is not observable. Okay. So I hope this example give you a J, different J's. So I hope you can follow the procedure, can tell the controllability, observability of the system. But of course, doing a rank for 2, 3 by 3 is difficult, right? Perhaps we only give you 2 by 2 blocks, okay? Blocks. So yeah. In fact, if you do not know this one, then it's difficult for you to figure out how to check, okay, how to check. So I hope you feel proud that you can do this. Okay? So today we are going to talk about Hautus tests. Okay? It's very specialized and much elegant, easy to use. So let's start for distinctive eigenvalues first. That's the easiest one. You can make A diagonalized. And even if your repeated, the eigenvalues are repeated, we can still use it. So, that's the beauty as well. So, but for easy representation, let's do distinctive eigenvalues first. So let's assume that left and right. So this is my left eigenvectors W, eigenvalues and eigenvectors. So this is okay. So left, not right. So we already learned that we want WB, okay, or we want WB, okay. I hope this W will make my B not controllable if and only if, okay. So this is very strong, okay. If we find out that WB is 0, and here is your eigenvalue. No, so I recall, okay. Do you see different? So they said S is any complex number, okay? They didn't say this is eigenvalue, okay? This is an eigenvalue. Be careful. And remember, this W is all the all the eigenvectors stacked together as a matrix. So this is n by n. This is also n by n. Okay. So this is a matrix. Okay. So this is n by n. This is n by n. S is a scalar complex number. You put S in here and put this W in here. So if you find out, any there exists at least one W to make this 0, then the whole thing will not be controllable. Okay, so that's kind of interesting. So again, remember, I'm not talking about eigenvectors, left eigenvectors. We're talking about the matrix W. It's a similarity transformation to make the A diagonalized. Okay, and S is a complex number. So we hope move this one to this side. I have the S in here. I just remember I just put WH in left side. I just put left side. So then I stack this one together. That's a column. Okay, column. So then if and only if this is 0. Okay, if only if this is 0. So in other words, this guy, the rank of this guy, is not fully ranked. At least fully low ranked. Okay, this is n by n. Okay, so this rank is less than n. When you add a b, that didn't help. Actually, it works. Okay, so in other words, this rank is less than n. And you can find out at least one S. Okay? But how I can find an S? This is too hard. There's infinite many. Okay, I'll talk about this one later. But now you remember, we argued so far, A and B metrics are considered as a controllable pair. Okay, controllable. If and only if this rank is fully raw rank. Okay, and remember, this is so hard. It's for all S you can see. So you need to check all of S. All of S, S is a complex number, C is a complex number. So this is actually useless. It's difficult to use, but it's very easy to prove uncontrollable. So you find one destroy this, then it's not controllable, isn't it? But if you want it controllable, then you need to find all of them. Did you see the difference? I hope you understand. This is actually useless to us to checking this controllability. But this is invented by Hautus called Controllability Metrics. Okay? This is very useful in polynomial matrix approach. The same thing can be proving that if A and C can be written this way, it's fully raw rank. Okay? Fully raw rank. Then it's called observable. This thing is called Hautus observability metrics. Okay. So I already made a comment that this is actually useless. You need to check all numbers in the complex. How can you do that? Okay. So the Hautus don't have to check all S. Only look at eigenvalues of A. So that is later on. They said, hey, if I can make if I can make Si minus A is rank, this one, if this rank is N, okay, don't have to check all of S, okay, only look at eigenvalues of A, eigenvalues of A. Then if put in that, then your rank is full rank, okay, then you don't really have to compute eigenvectors, okay? Remember, controllability, if you are given A, you need to diagonalize it or using Jordan block, then you check WB, right? Check WB. Check the WB. Matrix structure, then you check the rank in there and you can see whether it's controllable or not. So then this one, you don't have to compute eigenvectors, okay? And is always valid even if the eigenvalues are not distinctive, or can be repeating, okay? Can be repeating, okay? And you don't have to introduce the generalized eigenvector concept. So it's very rudimental, very rudimental. So I hope everybody understands. So then I want to say, oh, I have an eigenvalue. I have an eigenvalue. Distinctive or repeating, okay, doesn't matter. I just put it in, okay. Then this is a matrix giving AB. Then this is also a matrix. So just check whether this is fully raw rank. Then we can tell the model. It's called mode. Mode or model. Mode of controllability. I want to check whether this lambda I is a controllable mode or not. Why we call this as a mode? Because the time domain will always give you lambda IT, okay? Or if you have a repeating, then you have T e lambda T, right? Or Tk, okay, minus 1. So this is just modes, okay? Modes. So we have that mode. Same thing is true for eigenvalues. Observable or not, you check this one. Okay, sounds good? Sounds good. Hautus test and the mode controllability test or observability test, all can be done by using the Hautus test. So in the next, we have next we are going to go through a few examples. Okay. The first example we have seen this already. Is this controllable? Yeah, we can see this is controllable because B there's no row in the B is 0. Okay? But according to Hautus test, let's do it. Si minus B. Sorry, not minus B. Just stack with B. So you got a 2 by 3 matrix with parameter S. Okay. In this case, what do you say? What's the rank? That means no matter what S you put it in, the rank is always 2. Doesn't matter what S you put in. So this is easy to understand, right? This is easy to understand. Because you do have a diagonal in here. No matter you put S in here, that this is always different. Okay? So these are the same. It's okay to check. So you put a 0, so this is not 0. So anyway, this is easy to check by inspection. So you can, by doing that, you check all the S by inspecting. This is easy to tell. But you never know. But the good idea is I want to check my modes. If my mode 1 is controllable, I put in 1. So putting 1 is 0. Then you can see the rank is still 2. Okay? The rank is still 2. Because you cannot use a linear can use a linear combination to make a row completely zero. Okay, you cannot do that. So that's why rank is 2. The same thing, we put in lambda 2 is 2, so then this is 0, this is 1, so this obviously is 2. Okay? So the fully row rank means that you do algebraic combination of other rows and add to another one, can make the whole row 0. Then cancel out this row, so it's a rank deficiency. You cannot do that. Then it's fully column rank, fully row rank. Okay. So this is controllable. Make sense? Now, let's look at this one. We already know this is this is 1, 1. So this is easy. So what if I put this one 0? Okay. Put this one 0. We know this is not controllable. This is controllable. Overall, it's not controllable, right? So let's see the Hautus test. What's going to happen? So the same thing we can do S here, okay. What we can do is the rank here is 2. Okay, is 2. Is it 2? Can we make a full column all the column all 0 or full row all 0? We cannot. So it's still 2, right? So what's going on? What's going on? This is not controllable. Okay? Because this one is a rank deficiency. Okay? So you need to find out all the S in the complex plan to make this rank, okay, fully rank. So that's very difficult. You know that when S is 1, then the whole row is 0, okay? So then the rank is 1. So there exists an S make the rank less than 1. So this is not really right. So okay, this is true for S is not 1. Okay. So this one will be 0. Okay, like here. So this is like, if you find anything that is not fully ranked, you can destroy the controllability conclusion immediately. But to say, oh, this is fully controllable, you really need to check all the S. So let me go back to see what's the previous one. So previous one, the reason is, even if this is 0, you cannot make this thing whole 0, right? So this is 0, that means. So still valid. So I think we should change this one to 1. They don't allow me to edit. Okay. So I hope you understand Hautus argument using the rank deficiency to check uncontrollability is actually much easier if you put all the lambda in there. Okay. But on the other hand, if every mode is fully ranked, do you need to check S of other values? No need. As if you check all of them. So that's the trick. That's the good thing about mode controllability. You check every mode controllability is checked, then they are all controllable, then the system is controllable. So then you don't have to check all of S in the complex plan. So when you see the S in the complex plan, that's very scary. You know? be true for all S in here. It's very scary. You cannot do it. Okay. Let's see another example. Okay, so now you see something different. So this is, to me, I can recognize, but you will be able to tell immediately in next week. The controllable form and the observable form. So in this case, you have a -2, -1 as your ID values. Then we check about controllability gradient, its rank. B, A, B is this one and this one. B is 1, 1. A, B give you -2, -2. So the rank is 1. It's not controllable. Okay, but let's do a Hautus test. Okay, Hautus test. So for lambda 1 is -1. Okay, is S minus I. Okay, so Si minus A. Okay, and so first of all you put B in here and Si minus A. Okay, there's 2, 1, 0, 1. Okay, Si minus A. So they put lambda 1 is -2. Si minus A. Okay. So -2, -2. -2 minus 2 is 0. So -2. Okay. So this is 0 minus 0 is 0. So 0, 0. Then you have a 1 minus 1. So it's -2 plus 1. -2 minus, yes, 0s. So it's basically like S lambda 1 okay. So this minus this one will be 1, and here is -1. Okay. Then you add B, so it's 1, 1. Okay. Then this is a Hautus test for lambda 1. So the mode lambda 1 is controllable. The rank is 2. Okay. It's controllable. But lambda 2 will give you obviously is rank 1. So lambda 2 is not. Okay, it's not. So what does that mean? So using a simple LTI rank test or using a controllability gradient, you know it's not controllable, but you don't have insights about which mode is not controllable. You don't know that. Okay? Then the Hautus test is simple test that can tell you that. Of course, overall it's not. So this is just simple examples to enhance your concept. So there are more than one ways to check the controllability. So gradient, controllability test, controllability metrics, and then you can Hautus test. So they are all giving the same conclusion but with different insights. Let's check about Jordan form. Okay, so what's the algebraic? What's the algebraic multiplicity? 2. What is the geometric multiplicity? 1. Okay, so 1 block. So the Jordan form will give you the rank condition. So everything is 2. Then if you do lambda 1, lambda 2 are the same, put it there. You have what I said, lambda I minus A, lambda I minus A, and here you have B. Then this one is surely rank 2. now you see another idea here. So this is Jordan form, but you put this one 0. Okay? So lambda 1, lambda 2 is -1. Both. So then we do a rank. It's 1, 0 and -1, 0. Rank is 1, not controllable. So one of the reasons is you have 1, 0 here. This is B in the Hautus test. And you put S lambda I minus A and avoid this. So you have a pure 0 line. So this is a rank 1. So it's not controllable. It's consistent. But on the other hand, so if I switch, okay? If I switch, if this is 1, this is 0, okay? This is 1, this is 0. What's going to happen? Just everything is controllable. Remember, we said that in a Jordan block, the last, the WB, this is basically WB, okay? The WB is after transformation, WB here. The last row corresponding to the last row corresponding to Jordan block, it should be non-zero. Okay, then it's controllable. Okay, now it is not controllable. But if I put 1 here, 0 there, you flip it, then everything's controllable. Okay, so very surprising. Okay, very surprising. So we have gone through model controllability and observability, and to give us additional insights. And when we talk about input-output relationship in the transfer function, okay, so this, if it is controllable, then the independent of certain roles are transformed into the metrics. Basically, structurally speaking, we can focus on the WB metrics after the transformation, okay? WB. Okay. Of course, you need to learn how to do coordinate transformation to turn the original A matrix into J, and J is block diagonal. Okay. So observable if and only if those independence of certain columns are transformed. So this is certain. I think it's first column of each Jordan block. First column. The last row, okay? These are the rules, okay? First column, last row. But if you cannot remember that, it's fine, and you can borrow Hautus test. Directly you will be able to do that test. So I'm going to go quickly about discrete time systems. They are pretty much parallel. So then I hope to see a few exercises. See, instead of all facts and math. So I'm going to do discrete time and exercises. So basically we are ahead of time to finish. Okay. Oh, it's very ethical to mention Professor Doug Lewis. He's a professor at the University of Massachusetts, okay? UMass. And he created a lot of good slides. And this linear system slides, majority of them were prepared by him. And I did light edits. So we are doing, so in the weeks following, every Monday basically we'll add another hour to discuss our problem sets, okay? So good time is over. Huh? Every week we'll do 1 hour. So we're going to have a tutorial, not next week, but next week, okay? So midterm, yeah, I'm still thinking about midterm using a screen director. So we did modal controllability, we have done this. So talk about discrete time and then do some exercise we can finish today. Okay. Chapter 25 is discrete time. So let me remind you. This is a form, it's called discrete time linear time variant system. So A is a function of K is the sampling points, dots. Okay. We have learned that the response is written as transition matrix. It's like this. So if K is K0, you didn't do any jump, didn't do any transition. Otherwise, just from K0 transit to K-1. So it's a product. So this is phi. So then you can write down your state transition, the response of state due to initial state and control, written in this way. Okay. And J from K0 to K-1. This is a K. Okay. This is K. So this phi is taking this format. And output is C phi, and then you have C phi, BU, and DU. So just insert the K inside, because it doesn't matter, I'm not doing anything about K, I'm doing the J, okay? Summing up the J's. Okay, so controllability definition from time K0 to Kf interval, giving any initial state x0, you can always find a control such that you can move the state from x0 to xtf to 0. So they set this one to 0. It's the origin, okay? It's the origin. Okay. So it's the origin. So xk plus 1 is 0. Controllability, so controllable even though new control authority. Okay? Controllable even though new control authority. What does that mean? If you start with 0, you end up also 0. You didn't do anything. Any final state, so this is called reachable. So this is called controllable. Any of this you can find in the UT. So this is said you can find out the UT can move x0 to xtf to 0, giving xtf is 0. Okay. Now, I said giving any xf is not necessarily 0. You can find a control. You move from 0 from origin to any points. Okay. So let me draw that distinction. When I learned controllability and reachability, we didn't say that. So let me do a clarification for you. Okay. So in the 2D system, x1, x2. Okay. So this is origin. Okay. This is origin. And so supposedly you have a T0, you have K0, you are here, K0. Okay. So then you have a xk0 is already here. Okay. It may not be 0. Okay. It may not be 0. I hope you can find me a control. Move this K0 to any of the K0 to origin, okay? At given time TF, okay? Or KF, given time steps. Define a control for me. If we can always find it, this is called control, okay? Control. On the other hand, it's different to say, oh, I start from my xt0 start from is 0. Okay? Now I have any of the xtf is not 0. Can you find me a controller to make it happen? Okay? Okay, you can always find this one, this is called reachable to this, or reachability. But that doesn't really make me feel this is different. Reachability, controllability, to me they are the same, okay? So in other words, basically we want to make something here. Something here. This is something we don't like. The output K, we always write as the output K due to output K due to 0 initial state, meaning this x0 is 0. Okay? So this one is called zero state. Okay, actually, sorry. This is called 0 input. We don't have any input. I have this one. So this is called 0 state. Zero state. Okay. When this is x0 is 0, then this is the left. So we have two parts of the response. One is this is due to the initial condition. This is due to the control without the initial condition. So it's a 0 state, 0 input, 0 input. So the reason we talk about reachability, the question is to always make x0, 0. Always make x0, 0. Always make this one 0. So we don't care about this one. Because I start from 0, okay? So I can only focus on this one. So that's why it's more popular. But remember, when you do that, you are talking about reachability. Okay? Reachability. The controllability is different. Okay? I hope this clarifies. So unforced system goes to 0 in finite time. System can fail to be controllable in the ways not long enough. So this is an interesting and it's not reachable on 0 to 1. So you have reachable on 0 to 2. And you need 2 steps to reach. So in general, if you have n-dimensional system, you probably need n steps, okay? N steps to reach. So reachability means this R matrix, the B, phi B, and phi B. This is a transition, okay? Transition. This R matrix is fully low ranked, okay? So that's reachability testing. But this one corresponding to LTI system, time invariant, looks like exactly the same as we have here. This R matrix looks like this. Okay? So sometimes discrete reachability gradient is defined like this. And reachability gradient actually can be written as those controllability metrics R. Okay, controllability metrics R. So this is interesting, okay? Interesting. Observability, you have parallel idea here. So the rank of O matrix has to be something like that. Remember, this is called O matrix. So then observability gradient is if this is invertible. And again, we can write the observability metrics. Okay. LTI system, we have seen this one familiar. Okay. We also have seen something interesting like here. We are using a Z here. Z is also a complex number. But again, you need to check all of the Z, okay? All of the Z. Remember, we use S. there's no big difference here. They are the same. You can use S if you want. Okay, so I think in the next 20 minutes, let's work on some examples. I think I have shown this example to you. Okay. So, is there any questions about discrete time system? I think it's very parallel. All you need to remember to see is something different in here. One is called R matrix. Okay, R matrix. Another one is called O matrix. O matrix, okay? O matrix. So this is also called observability metrics. But remember, observability metrics is not observability gremium, okay? But they are connected. Observability gremium is written this way, but there's the composition of this one. So this is actually beautiful. So when you write something you have seen before, like A, you do AB, A squared B, you can do that. A minus 1. So this is actually, people call this is controllability metrics. Okay? Controllability metrics. But it's not controllability gremium. Okay, it's different. So LTI system is like that. So we have a Hautus test similar in here, and you need a full column rank of this O matrix. We have seen this before in continuous time, very similar. Well, I want to go through a few examples with you today. We have quite a lot of examples put together. So the first example is linear time varying system. You have a A1, A2 diagonalized. So then we assume that B1, B2, A1, A2 are not equal, they are not equal, they are not zero, okay, zero. And we have B1, B2 is A to the power of K, A2 to the power of K. So these are the discrete time system, okay, discrete time system, time invariant. So then this state, this is a controllability matrix. It will give us A times B, A, okay, is I think this is B, this is B, right? So then we have this connection. So you will see that because of that, B1K is A1K power of K. Then you multiply A1 is K plus 1. So then you always get something like this, okay? And this row and this row are the same, okay? Are the same. So therefore, we know that for freezing coefficient point of view, for any fixed K, it's controllable. It's controllable, but overall, it is not. So if you use time invariant thinking to think about time varying case, it could lead you to wrong conclusion. Make sense? Okay. So those are discrete examples. The first one I have seen, we have seen this before. Okay. I remember I explained to you. So let's see another example. Okay. Another example. So this is an example for linear. It's actually a non-linear steady equation. Okay, steady equation. So in the chapter 25, they said in this example we show that this is an LTI system. It's three input, one output. Okay. So the B matrix from here is invertible. So this is regarding a birth rate and survival coefficient. So let me go back to give you the background about 20.6 example, 10.16. Linear steady equation in terms of deviation from a nominal solution. So then you can get a linearized system, okay, linearized system. So this is economic model, example 20.1. You can have a constant government expenditure, GK is G, and corresponding constant nominal solution. Based on that, you can write this way, 2x2 system. Okay. So this is exactly what we are trying to do here. And around the nominal solution, let's get these changes. Then in the changes, we write LTI system. So this is our LTI system. Okay. There are some deeper discussions here regarding why we do this. Okay, so it's because otherwise your state cannot be negative, so you become a non-negative system. Because your government expenditure, you always spend it, you don't get, okay? Economic model. So those expenditures, okay? So you cannot change the sign of the variable. But to change back, you need a nominal. So you can be positive or negative around the nominal. So that's the main purpose of the modeling exchange the variables, okay? Let's still focus on this one. This called national economy, okay? National economy, let's focus on that. So this X delta, I just showed you how they come from time varying nonlinear system. But now this is an LTI system. Alpha, 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 beta, alpha. All signals are permitted to take either positive or negative value because of that change, the delta. So you can fluctuate around the nominal. Okay? So now the key question is whether the government spending, GK, the spending, can be used to reach any desired value. It's a controllability question. Within a range of modulability and the state variables, consumer expenditure, and private investment. Third one, third two here. So then, to answer that kind of, whether the government spending can be used as a tool or authority to change consumer expenditure and private investment. So to answer this question, you basically need to answer whether VAB, this is raw ranked, okay? So you end up with this one. So this reachability matrix cannot be zero for any coefficient alpha in here, beta greater than zero. So that's good, okay? That's very good. Then let's check observability. So you can see observability, controllability, they can help us to answer many interesting questions like we raised in here. So let me read it for you. A question of interest, whether the government spending here, okay, can be used to reach any desired value, again within the range of modulability, validity of the state variables. The state variables, one is consumer expenditure, private investment. Okay. So this example 20.16 is there. So we have peace of mind. Yes, government can do it. It's controllable and it's reachable. Then, whether the knowledge of the national income, this is national income, YK, add together is add together. So what add together? Private investment and consumer expenditure. Add together is the national income. So the national income Y for successive years can be used to ascertain the consumer expenditure and private investment. This actually amounts to answering a question of observability. Then we do CECA, we get this one, greater than 0 is fully ranked, so yes, it's observable. So that kind of simple argument in real world, you can use controllability observability to answer many interesting questions, okay? So here's another example I put here for you. It's called example 22.16 to talk about cohort population model. Okay, reachability property of years below for 16. So reachability is B matrix invertible. So that if the birth rate and survival coefficient are combined or positive, they interpret saying that desired population distribution can be obtained by selection of the immigration levels in any single age group. Okay, so again, this is talking about reachability metrics. Okay. So go and these are the observability metrics. So you can see for this physical system, okay, it's called cohort population model. Then you can see very interestingly, there are controllability and observability can help us to answer interesting questions. I'm not going to go to the details here for you. Okay. So let me see, I still have quite a lot of slides. Oh. This is the part I think is more important for everyone here. So let me go to a SISO system. Okay, you have A and B, so this is a continuous time system. You know that if you are doing sampling, and the sampling period is T, everybody knows that using simple integration, you know that starting from KT, how you can get K plus 1T, is basically 0 to T to do this integration. Okay. So then we're talking about n by n matrix of this one. Okay, this is my B. And the EAT is 5, okay, this one, and here. We hope this invertible. Invertible. So on the other hand, if you can find any two numbers, R and Q, in this range, make this one equal, then this will not be invertible, will lose rank, okay? So if original system is fully ranked, is invertible, after discretization, then this reachability could be lost. Okay? This is serious. So I want to alert you, okay? So you have a continuous system, you sample it, then you are working with a discrete time system. So the continuous time system is controllable, but your discrete time system may not be, surprisingly. Okay, so you need to have an extra care. Okay, so loss of reachability on the sampling can occur. Can occur, is not could occur. Let's see an example, okay? So this is a system, okay? Is this controllable? This is of course controllable, okay? So then this is output in the continuous time. So a discrete has this one. This is e to the power of at. Okay? So then you have B matrix is like this. Okay. So if you have any like pi in here, this is 0. This is also 0. So if your capital T, the sampling period is at the wrong value, then your control authority are totally lost, as if the system is out of your control. Okay, so that's all possible. Okay, so but this one is actually showing you why you have this magic stuff is because of this one here. So A is this matrix. Then state transition matrix is by inverting this one. So this is Si minus A inverse. Then this inverse to inverse Laplace transform. So S divided by S squared plus 1 is cosine T. 1 over S squared plus 1 is sine T, and minus sine T cosine T. So that is my EAT. Because of that is in chapter 5. Then we'll put it in. So this is EAT, XT. Given kt, then what is k plus 1t? So then this is the b. So let me go back a slide one more time. What is the b? B is this matrix, integrating 0 to capital T. Okay? And this EAT is already known. Okay? So it's here, this EAT. This is integration of the EAT go back. EA tau and B and D tau. Okay, so then we end up with this one. So this is new B matrix for discrete time. So this is A matrix in discrete time. If T is wrong, capital T is wrong, your T is chosen by you, right? You choose the T. If the T is not right, this is not controllable, not reachable. And the same idea, observability could be lost for the same value of T. So if you same value of T, then this is also not not observable. Okay, not observable. So I hope this one can give you an alert. It's not guaranteed. No guarantee. So, but in general, there is a mechanism called holding mechanism. So you are at a time k capital T, you have k capital T, your sampling period is capital T, and in between k plus 1t, so it's not like, your signal is not like this. So you have a k minus 1, k and k plus 1. It's not like a dot. It's not like a dot. Okay? It's not like discrete like that. In reality, you hold it, then you hold it, you hold it. So this is called holder. Okay? It's called a zeroth order holder. So basically, this equation is a mathematical representation of the zeroth order holder. So the V is a holded. The V is a holded version of the U. Okay, U is a discrete point because we only live with the K. So I have UK. Okay, UK, but the K is not time, K is points, number of points. So the real time is K times T. Okay, this is time. So at that time, but you have a You probably have a continuous version, but in discrete time, I don't care. I don't have it. Okay, I don't have it. So this is dot. This is also dot. The same. It's the same dot. But it should be understood in a different way. Okay, this is a sequence. This is a continuous. But in reality, a lot of people say, "Oh, this is a discrete sequence. Then let's put into the VK in such a way. Hold it, hold it." So that is basically I'm holding it. So if you hold it, then our system will be a little bit different. So you can see the output is transitioning here, from KT to K+1T integrate. But because I hold it, so this is UK here, I hold it, UK plus 1 is a constant, So then, is a constant. So in other words, because of the constant, then you can write matrix exponential like this, So you can turn to the linear time invariant system very easy. Okay, very easy. So I'm running out of my slides. So we are going to do next time about canonic decomposition. Okay, so next time we are going to do canonic decomposition. So I hope, starting from today, we are going to think about, you have AX plus BU, okay, X plus BU. So you know that we can doing similarity transformation, so that we can write Z is WBU, okay, WBU. So in the next, we're going to talk about this canonic form when these variables are not minimum. Meaning I have used more than needed variables to describe the state space, okay? And then we are going to see the state space can be partitioned into 4 parts. One is controllable, observable, controllable, controllable, not observable, and not controllable, observable, not controllable, not observable. So we assume always here, but in reality it may not be true. For that, how we are going to decompose it? So giving a, so how we can decompose it, okay, distinguish it. So that part is also called Kalman decomposition. So if you do not know how to do this, then you can say you know how to do minor. That's, you have the way to zoom in to see the essence of the structures of the state space description of the linear system. So we take 5 minutes break, then we'll come back.